Wow. Hey, welcome everyone. GOBC Chem 114. We're into amines just a little bit ago. Now we're going to get into amides, which is kind of like amines, but now we're going to take what we know about a carboxylic acid, and instead of having hydroxyl next to it, we're going to have a nitrogen group. So not that much different, but it is different. And let's get started. So, amides, where are they located? Well, where can we find an amide? Aspirin doesn't have an amide in it, but acetaminophen, which is sort of like an aspirin substitute, except it does reduce fever and pain, but it doesn't do very good for anti-inflammatory effect. At least that's what they say. And an anti-inflammatory effect is more swelling. So if you have swelling and you're not allergic to aspirin, that's probably the drug of choice. But aspirin does not have a amide in it. And where is the amide here, by the way? The amide, I'm going to circle it. Of course, okay, there it is. And so there we have the carbonyl group, and now we have the nitrogen instead of an oxygen being attached there. So um, a little bit different. So we're going to call that an amide linkage. Now, this is the name for the drug acetaminophen, which is a drug we can buy without prescription. And so let's take a look at carboxylic acids and see how we transition into a mid. So we have some kind of connecting point because we know what carboxylic acids are now. We learned how to make esters, didn't we? We learned how to use alcohols and react them with carboxylic acids, and we get esters that smell really nice. Um, we can, if we get rid of this hydroxyl and we attach a NH2 group and we kind of say, well, that's sort of like a primary amine. That's true, but more than that, it's an amide. And if we, again, just to circle that, there's the amide group, right? And it has unique properties here that, remember, there's a lone pair on nitrogen, there's two lone pairs on oxygen. Guess what? This is very stable because these lone pairs can migrate here, and then this pi bond here can migrate up there. And what does that look like anyhow? So what am I talking about? So the double bond is gone to the oxygen, it's left, and now we have three lone pairs of three lone pairs of electrons on oxygen, and now we have a carbon double bond um, nitrogen, such as that there. And that, of course, will put a positive charge on nitrogen and a negative charge on the oxygen. Now, this is not as common as this because why? Well, we put charges on these elements, and when elements or molecules can go without charges and there's a choice by moving lone pair electrons around, it typically wants to get rid of the charges. So this, what we initially looked at, this amide is typically how it looks. This is a very small part of the molecule. So we have carboxylic acids are sort of like amides, aren't they? And we look at the name here. We call this ethanoic acid, and the common name acetic acid, which is vinegar. But we can call this one um, ethanamide because we have two carbons, which is from ethanol, but we're not an acid, we're not an alcohol, we're an amide. We're not an amine either because we're next to a carbonyl, so we are an ethanamide, which is an acetamide, which is the common name, acetamide. You might hear that a lot. So moving on, amidation. What in the heck is that? Well, let's suppose we learned about carboxylic acids as a reference, but we can react carboxylic acids with ammonia and get, guess what? Amides. For example, if we take propanoic acid, we react it with ammonia, a base, and we have some heat, we have to provide heat, and then we will get propanamide, which is a amide, and we get a dehydration reaction because we're going to lose water here. Where will we lose water? It should be obvious. We're going to lose water right there, and that's going to come off. Water's going to come off, and we're going to have propanamide. So we can make amides from carboxylic acids and ammonia. But we don't just have to stick with ammonia. We can get fancy and we can try methylamine, right? Methylamine has one carbon on it, which is a methyl group. And so we can react the same starting material, the propanoic acid, with that carboxylic acid with this methylamine, a little bit of heat, and guess what? We now get N-methylpropanamide. And looking at that, you might say, well, how do I deal with that, Mr. Pryor? Well, okay, we have the root. The root is going to be the propanamide, okay, which came from this. And then we added methyl group, and we know that the N-methyl group, and we know that the nitrogen contains that methyl group, so we call it N-methylpropionamide. Okay, so we're kind of using the same thing we did with carboxylic acids, right? And as the parent, and then we're adding N-methyl to that because that's what's comes along with the nitrogen. And we made an amide. So we turned a carboxylic acid using ammonium or a primary amine into an amide through this reaction. Amidation, they call this. And you should know how this works. Well, now that we know a few things, say we take benzoic acid. We take benzoic acid and we react it with methylamine. Um, so as you can figure out, we're going to guess that this nitrogen is going to come over here and attack this carbon, and we're going to end up losing water here, and we're going to get an amide, and we're going to get a dehydration reaction as well. And so guess what? Exactly. So we get this benzoic acid which ends up becoming a N-methylbenzamide, amidation reaction, and we can do this. So we know we have some more tools in our reaction uh, toolkit, so to speak. And um, now we could just look at an amide and kind of figure out what we started with, right? We kind of can cut it in half and we could say, well, this was probably a carboxylic acid, so there was an OH here. So that must have came from butanoic acid. And here we see the name of this of NN-dimethylbutanamide. And the NN comes from the what must have happened here is we reacted with the secondary amine, which was HNCH3 2, and we reacted that with this carboxylic acid, and we got this what they call NN dimethylbutanamide, or we can call it NN dimethylbutyramide. So, yeah, we should kind of know what that N is for. What does that N mean? That N, the N, just the letter N stands for, you use that as a designation to what's attached to the nitrogen group as opposed to what came from the carboxylic acid group. And since there's two groups attached to that nitrogen, we call it NN dimethyl. Okay, so you don't get that confused and think it's attached somewhere on the acid part. You know that it's attached to the nitrogen directly by that NN dimethylbutanamide. So the butanoic acid becomes, instead of butanoic, it becomes butanamide, right? Butanamide. Okay. Um, Looking at this, we see 3 carbons on this side, 4 carbons with the carbonyl, and then we see NHCH3. So we kind of know that it's got 4 carbons, and if that's the case, then we're dealing with probably came from butanoic acid. All right. And then we have this nitrogen, a hydrogen, and a methyl group. So we know we're dealing with probably came from a primary amine, which reacted with this carboxylic acid. And so when we write this, we'll have to say, okay, as the parent name, we're going to want to call this butanamide, right? Because it has, instead of butanoic acid, it's going to be butanamide because we got to account that now it's an amide, not a carboxylic acid. But then we have to look at this and say, well, this is going to be N-methyl. So we're going to have N-methyl butaanimide. And let's see, we're right. We get butaanimide as the parent. And then we have to add the N-methyl to the front of that, N-methyl butaanimide. So not a surprise. Hopefully that makes sense. Review the rules if it doesn't. Okay, what do we have here? Looks like amides. Here we just have a methyl and a carbonyl, so we probably have something like this came from ethanoic acid, so we have an ethanamide, and we have an ethylamide, and we don't have anything attached to this nitrogen, so that should be good. Uh, then on B, we have 1, 2, 3, so that's going to be propanoic acid that it came from, so it's going to be propanamide, but we also have to account for this N-ethyl, so this is going to be N-ethyl propanamide. Let's see how we did there. So this is just simply ethylamide, or it can also be called acetamide. And this is N-ethyl propamide, which makes sense because this is ethyl and this came from propanoic acid. So N-ethyl propamide is the correct name. And now let's get to something kind of interesting. Urea is something that we dispose of out of our bodies from protein metabolism. It's excreted in the urine. It can be toxic. If it becomes toxic, if we can't get it out of our system, we could suffer from uremia or uremia. And urea is also used in fertilizers and things and such. It is, as you can see, nitrogen intense. And we get this because proteins are filled with nitrogens and our nucleotides are filled with nitrogens and we have carbonyls in our body. So this is a byproduct of that. And sometimes our body can reuse urea, but if we create excess, the body has to get rid of it. And moving on to barbiturates, and what do they do? Well, they're sedatives. They help people sleep. They can unfortunately be habit forming, just like caffeine. We have a couple different type of barbiturates, such as luminol and nebutyl, and they're a little bit different and a little bit similar, right? This ring kind of looks the same, but here we have a chain, and here we have a benzyl ring. So they people respond differently to the drug. Some people, they have no effect from certain drugs or they're allergic. So we have these alternatives that may be helpful as a sedative or to even help provide needed sleep. So aspirin substitutes include phenacetin and acetaminophen, and you can see amides are in both of these. Again, neither one has the anti-inflammatory activity that aspirin has, as well as the fever and pain reduction that both of these do provide. Hydrolysis of amides. So say we want to break these apart and we want to restore the previous carboxylic acid and the amine that we had. So we can go and we can do it two ways. We can add a strong acid or we can add a strong base, and either one will work. The result is a little bit different, and you should start to kind of have an appreciation for the result. Um, Here we have acid, and we're able to protonate this and cause this to break up, and we get the carboxylic acid back, and we get the ammonium chloride, but it's protonated because we probably added excess HCl. So the carboxylic acid is completely protonated, as well as the ammonium salt. Now, if we do the amide and we do a sodium hydroxide hydrolysis and heat, we can break this up as well. But since we're in base, we're going to deprotonate that acid, right? Because if we add sodium hydroxide here, we get rid of the proton, and we would get rid of this extra proton on this ammonium chloride. So this is not unexpected. We get sodium propanoate because of deprotonation by the base. We probably added excess base here. Then methylamine, of course, is not protonated. The lone pair of electrons, it's in base media, so it's not going to protonate as if it was in an acid because we're in base media. So this makes sense. If this doesn't make sense, come see me, talk to me. Why, if it doesn't make sense, let me see if I can help you with that. Um, Moving forward, you can run through this metacognition. Um, Here they're just showing how they divide this, and base hydrolysis is going to how that's going to work here. And what are we going to break this down into? We're going to have to add a proton here, and we're going to have to add a hydroxyl here. So we end up with sodium pentonate and methylamine, all starting from the N-methylpentaamide that we hydrolyzed with base. So you should be able to understand these components, how this amide, this N-methylpentaamide, was broken down with base and heat. Now let's see, draw these structures, pentaamide. So we know that this is going to have 5 carbons, and then it's going to have carbonyl, 5 carbons with the carbonyl, and then a nitrogen H2 right next to it. So this one kind of makes sense. N-ethylbenzamide, well, benzamide, we're going to have that ring. So we know we're going to have a ring there, and we're going to have a nitrogen attached to that ring, and then there's going to be an ethyl group off that nitrogen and a hydrogen and the other nitrogen attached, or not the other nitrogen, but the nitrogen attached to the ring, ethyl attached to the nitrogen, and so on. Let's see how that looks. Exactly as we would expect. We have benzoamide, which came from benzaldehyde. So we have this carbonyl, and we have the nitrogen attached here, which accounts for the amide. So the nitrogen is not attached to the ring, excuse me. It's attached, since it's benzaldehyde that it came from. And if we were to, or benzoic acid. So if we were to think of the starting material here, we have the circles. The circle's the same as that. We would have the carbon, the double bonded oxygen, and the carboxylic acid. And of course, this would have been a primary amine, which would have been um, an ethylamine that we would have had here. So finally, this is a terrific table to really tell you the story of what we've just learned, to summarize it all up so you can feel confident that amines have nitrogen atoms. They're bonded possibly to alkyl or even aromatic groups such as benzene. They're soluble in water up to 6 carbon atoms. After that, they're not very soluble. Amines can be weak bases, just like ammonia, and they react with acids, as you would expect, as um, a base reacting with an acid can lead to neutralization or acidifying it. You can form amides, and amides, as we learned, they come from these carboxylic acids, which have a carboxyl group. They're soluble up to 5 or 6 carbons. The carboxylic acids are, of course, polar. They're weak acids, such as vinegar. They're neutralized. You can take a carboxylic acid and neutralize it with a strong base, and you get carboxylate salts. You can take carboxylic acids and react them with alcohols, and you'll get esters. And then you can use saponification to break down that ester into a carboxylic salt and alcohol. And then we have the amides, of course, which react with amines and a carboxylic acid, an acid and a base. You get carboxylic acids and ammonium salts if you use acid, or you get the carboxylate salt and the amines if you break down the amides through a base. So you should understand how amides are made from carboxylic acids and amines, and your previous learning for carboxylic acids is useful. This has been another Chem 114 General Organic and Biological Chemistry, and I will see you guys soon. Take care.